just a really quick note before I get into anything at all with the lesson itself. And that's that this lesson comes with a handout that has basically some fill in the blank stuff and some preset up graph grids and information that you may find easier to do than just taking notes all by yourself. So go download that and use it now. Welcome back. Okay, so in our last lesson, we took a look at z-scores, which finishes off pretty much everything to do with one variable statistics. One variable statistics is really about measuring one thing from a bunch of different things in our sample or population and taking a look at things like central tendency and how far apart those data points are spread out. So that's what one variable statistics is all about. In two variable statistics, which is what we're starting today, we're going to look at how two things are linked to each other. So this title slide, for instance, it's looking at how two things, the mean seen level and the year, are related to each other. So it's basically saying, is there a link between those two variables? And if there is, can I find a pattern? Now, we're going to talk more about this again later when we get to the slide on correlation versus regression, because there are two things that often get used interchangeably, and they actually mean drastically different things. Correlation is really, is there a pattern shown between the two variables, and how good is that pattern? So that's what all these little dots on this graph are. When I move from left to right, I see that there's a decent pattern forming between those dots. I can kind of see where the next dots, like if this graph was to continue on, it only goes up to 2011, but if it went up to our current year, I could probably guess roughly where it's heading. I can guess where the dots are going to be. So there does seem to be a pattern. And then the regression part of it is, can we find a mathematical function to represent the pattern that we're seeing? So in this case, it's a straight line. Can we find the equation for that line? So one of them is saying, is there a pattern? And one of them saying, what's the mathematical representation of that pattern? All right, so as I already mentioned, one variable statistics, which we're now done with, has to do with looking at things like, what's the central tendency, what's the spread. When it comes to two variable statistics, looking for links between two things. We're hoping in many cases that there is a link between two things, or sometimes in mathematics, we want to prove that there is not a link between two things. And two variable statistics will allow us to do that. And the tool that we typically use for two variable statistics, which you've probably encountered at least a few times before in your life, probably in science class, possibly in lower levels of math, hopefully in both, would be something called a scatter plot. And it's basically just we set up a grid and we plot a bunch of points on it, and then we look to see, is there a pattern in those points? Are they forming some sort of obvious picture? We often refer to the independent dependent variables. The independent variable is usually the value we choose or the value that is set that we have very little control over. And that's usually what goes on the x-axis or the horizontal axis. And then we have our dependent variable, which is the thing that is usually affected by the independent variable. And we usually put that on the y or vertical axis. Now, I should point out that there are lots of studies that you might do where you don't know which variable is dependent, independent, in which case you take your best guess. It's usually the one that sounds like it makes the most sense. So if we take a look at that little graph in the bottom corner there, across the horizontal axis, we have years of experience. And across the vertical axis, we have income in thousands of dollars. At least I'm assuming it's in dollars. It could be in pounds or, I don't know, yen or something like that, but it's probably in dollars since the rest of the thing's in English. Does it make sense that your income would change based on your years of experience? So my years of experience, I don't think are going to be affected by my income. No one's going to come along and say, wow, you just got a raise. You must have worked here longer now. They're going to say, oh, you've worked here for a while. That's why you're getting a raise. You've gone up in value. So I'm going to use this example on cars. If you're not a car person, please just bear with me. At least the cars that I'm talking about in here are nice and pretty ones. They're all my favorite old classic muscle cars. I'm a huge fan of classic muscle cars. I'm a huge fan of all muscle cars. I like nice cars, period. Not the expensive like Bugattis and stuff. That's just anyone can spend $1 million to get a nice car. I'm talking about like nice cars for the average Joe or Jane. I shouldn't be sexist. So here's an interesting little background to these cars. And that's that in the when they were first kind of becoming popular in the 60s and 70s, the horsepower ratings that they had were normally advertised lower than they really were, which by today's standards seems crazy. I mean, today they try and do everything they can to overemphasize how much horsepower a car has. They'll always round up. They'll find out what the fastest speed was, not telling you that it was going downhill in a near free fall, like stuff like that. But in the old days, when they first came out with these, they set the advertised horsepower as much lower than it was, or at least somewhat lower than it was, so that it would keep your insurance rates lower, and so that when they were doing drag races or like racing meets, you could be entered into a category that you were probably overpowered for. So for instance, here we have a Camaro Z28, gorgeous car. You might recognize this one from being the Bumblebee in, I think it was the third movie. Well, it would be if at least if it was yellow with black stripes. But the Z28 was advertised as 290 horsepower, despite the fact that it had 310 horsepower. So what that means is the person who bought this got to save a little bit on insurance, and they could enter into drag races that were horsepowered up to 300 horsepower. So even they were actually a little bit overpowered for their class. Now, everyone did this, so it didn't really matter. But if anyone just said, no, we're being honest, then their cars would lose all the races. So they never said that. So we have advertised horsepower, and then we have real horsepower. We're going to use those as our two variables. So how much they said it had versus how much it did have. Now I'm going to read these following two statements. I want you to listen to them carefully and think about them and tell me which one makes more sense, because that will tell you which one the independent variable is and which one the dependent variable is. So statement one, the actual horsepower determines what the advertised horsepower will be. So the advertising agent says, okay, I know what the horsepower is. This is what I'm going to advertise it at. That seems to make sense. The second one says, advertised horsepower determines what the actual horsepower will be. So that's like me walking up to a car and saying, hey, you're 800 horsepower. And then the car is all of a sudden a higher horsepower than it was before. Your advertising changed what the car actually does. Okay, that seems kind of ridiculous. So I think we're going to go with the first statement. The actual horsepower determines the advertising horsepower. So actual horsepower is independent. It is what it is. Advertised horsepower is dependent on what the actual horsepower is. I think I said that right. I hope I said that right. Okay, so here we have a bunch of different cars, a bunch of 60s and 70s muscle cars, and we have their actual horsepowers and their advertised horsepowers. And the good news is you don't really need to understand what these cars are. Just be aware that they're all different vehicles, with the exception of actually the Mopars, which are not specifically a vehicle as a type of engine which appeared in several vehicles. That aside, all you really need to understand is different cars, actual horsepowers, advertised horsepowers. So I'm gonna make your life a little easier. Use the handout to do all these with the pre-made graphs and all that stuff, but we're gonna walk through this question. So first thing you're gonna do is take your scatter plot, your blank scatter plot on your sheet, and you're going to plot all the actual values that were given on that table. So throughout this, whenever I tell you to do something, briefly take a moment, pause it, the video, go try this, and then come back when you're done and continue. So I'm going to make the assumption that you've stopped the video and made the scatter plot. And once you've done the scatter plot, it should look a little bit like this. Now, a fairly common question that I get, and may have come up, is that what happens if I've got two data points that are exactly the same and they overlap? Now, I'll be honest, I'm using an actual program to make mine, so it doesn't do this. But what you can do on a handmade plot, and what some programs will do, is make the dot a little bit larger if there's like two dots on top of each other. And what it does is draws your eye and says that is a more significant point than the others. So it's basically two data points on top of themselves. So that's what your scatter plot should look like. Now let's talk about what we're going to do with it. So as we mentioned before in the title slide, there's two things that we want to worry about or think about here, and that's correlation and regression. So the correlation is if you see a relationship, you see some sort of pattern in those dots. I'm just going to go back for a moment. And despite the fact that I haven't drawn any lines yet, I do see a bit of a pattern here. I see what appears to be numbers going from the bottom left towards the top right. I definitely see that there's a pattern there. In the next lesson, we're going to take a look at measuring correlation, which basically says how strong it is, and it's how obvious that pattern is. So here, I'd say the pattern's relatively obvious. It's not super, super obvious. There are dots all over the place. And if I look at, for instance, 410 actual horsepower, there's 3 different advertised horsepowers for that. So it doesn't definitively tell you one from the other, but I do see a pattern. Now the regression, another term for regression that you've used before is a line of best fit, which is an example of linear regression. Regression's finding an equation or a function that represents the actual path that data follows. So you've done lines of best fit for linear regression. And what we're going to do in this course actually is more linear regression because the others are a little bit harder. But I want to point out that we can use things like Excel or other spreadsheets to do calculations on nonlinear regression. So we could do parabolic regression or exponential regression or logarithmic regression. And there's all kinds of stuff. And you could even do, for instance, if you've taken functions, you may have done a little bit of trigonometric regression. A little bit harder to do, but the idea is still there. Now, a misconception that I often hear, and it bothers me to my deepest of cores, is that when you're doing a line of best fit, you should always try to ensure that there are the same number of data points above it and below it. And that's not necessarily true. I don't want you to think of above or below. I want you to think of what line do you think best represents the data points that you see. I'm going to go back to the scatter plot for just a moment without the lines on it. Pretend that this is a bird's eye view map of like a playground. And that these are, I don't know, pieces of bubble gum that some kid left behind that was falling out of their pockets. Could you try and figure a line that best represents the likely path of that child? That's really what regression's about. It's not about ensuring equal balance above below. It's about trying to find the path that best represents what's happening. Okay. So when you're doing a hand-drawn version of a line of best fit, again, you just try and do a line that you think best represents the data. Now, I've put mine on here. Yours might be a little wee bit different. So I'm going to make note that my x-intercept looks like it occurs at about 265, and my y-intercept is actually not on the graph. It goes off the graph over here on the right-hand side at about, what are we at, 450, 460, 468-ish. If yours is a little bit higher or a little bit lower, that's okay. If yours is quite a bit off this, a couple things you can do is cover up half of the graph, the left half or the right half, and see if all the points still look like they're kind of best fit for that line. If you notice that all the points on one side are too low and all the points on the other side are too high, it means your slope is a problem. If you notice there's way too many points above or below, it means your basically translation up and down is a problem, so you can slide it up or down a little. And once you've got the slide up and down and the slope correct, you should be good to go. So finding the line of best fit, which is our next obvious thing to do, also because the slide says so. We want to find an equation in the form of y equals mx plus b, which is our standard linear equation. And there's something you can do called the least squares method. This is actually what spreadsheets do. what they're trying to do is figure out how far each point would be off a line, square that distance, and then find a minimum of all those squares put together. The reason for that is if two things are, or if a few points are way off the line, one above, one below, just looking at the distances doesn't really tell you a lot of information. Anyway, that's more than we need to worry about. So if you look at this equation here, the slope of our y equals mx plus b equation is going to be equal n times the sum of all the x values times their y values put together. So basically from our data table, we take our x value times our y value, and then we add up that for every single car. Then we subtract off all of the x values added together times all of the y values multiplied or added together separately. And then on the bottom, we square the x's, add them together, multiply by the number of data points, and then subtract the sum of the x's all squared. Now, to be really clear on the bottom there, one of them says square then add, one of them says add then square. So BEDMAS says those are different things. And then if we want to find our value for b, our y-intercept, we say the add up all the y values, divide by the number of data points, subtract m, which we just calculated, multiply by the sum of all x's divided by n. Okay, so once you've done all that, you first of all are going to have a horrible headache, especially if there's more than like 3 or 4 data points, because this is a tedious procedure. And you're probably going to have to file for like old age pension at that point, because it takes a while to do this calculation, which is why we are not going to use this method. This is what the spreadsheet does. It's not what we as human beings are going to do. I just want to point out that we could. There is a formula for it. It's just a long, tedious formula. So what we're going to do is slightly less exact, but it is basically the way that you've been dealing with it since you were in grade 9. And that's draw the scatter plot, put your line of best fit on it, and then from your line of best fit, not from the data points anymore, once you've got your line of best fit, pretend the data points aren't even there. You don't want to touch them. Pick 2 points on the line, not 2 of the data points that happen to be on the line or close to the line, just 2 points that actually fall on the line, even if they're not data points, especially if they aren't data points. Do not use data points. Pick 2 points on the line, find the slope between those 2 points, use one of the points on it to find the equation. So basically exactly what you did in grade 9. Okay, so from our muscle car scatter plot, we want to draw the line of best fit and find the equation using the easy method. So on my graph, there's the line of best fit on there, and the 2 points that I've chosen are not data points. And ideally, they're 2 points that are fairly far apart. And the reason for that is when they're far apart and off by a little bit, it doesn't make a big difference. If you pick 2 things too close together and one of them's off by a little bit, it can actually create a significant change in slope. But anyway, try to pick 2 points that are relatively far apart. Okay, our left end point is 263, 250. And again, maybe it's 254 or 264 or 262. I don't know. But it shouldn't make much of a difference. It'll actually keep our slope pretty consistent, even if it's off by a little bit. And the other endpoint I'm going to use is 550, 468. If your graph's a little bit different, use your numbers. Use your numbers, it should be fine. So then I say, okay, those are my 2 endpoints. My slope is just the change of y over the change of x. And you might have seen this equation as y2 minus y1 over x2 minus x1, same thing, same difference. Either way, rise over run, and you should get a slope out that's somewhere in the ballpark of 0.76. Now, I'm going to say mine's better than yours, or more close to the correct answer compared to yours, not because I'm better at this than you are, but because I actually had Excel draw the proper line of best fit for me and then went over it with a manual line, just to make sure that I had the best possible example to show you. However, I did do the calculation manually. So the calculation is a real approximation. The only difference is my line of best fit was drawn quite well, essentially. Okay, so I have my slope. I then take my slope, plug it into my equation as the m, along with one of the 2 points. In this case, I chose to plug in the x equals 263 and the y equals 250, and solve for your b. Once you have that, you've got the equation of your line of best fit. In this case, mine's 0.76x plus 50. Yours might be a little bit different. I should point out that the slope for yours should be probably fairly close to mine. The intercept may not be. I'm going to go back for a second and show you why the intersect may not be. So on this graph, if I ask people to tell me what the y-intercept is, most people will tell me, oh, well, it goes below what's there, so, but I'm going to guess it's around 240. Well, remember that the x-intercept actually appears where x, or appears when y, or it's the y value when x is 0. But since this graph actually starts at x equals 250, we have to go 250 further to the left before we actually get to the true y-axis. It looks like the y-axis is on the left side of this sheet, but it's the true y-axis is actually way, way over. And because of that, it's much lower than we thought it would be. So don't try and estimate the y-intercept from the graph unless it's actually got an x equals 0 on it. Okay, so our approximated from our 2-point method, 2 points, find the slope, find the equation, was 0.76x plus 50. And if I put this data into Excel, which I did, it actually calculated to be 0.7599x plus 50.001. I would say that's pretty good. And if you did it the long way with the big equation, the nasty equation, that would be the answer you'd get, at least to 3 or 4 significant digits, which is more than accurate enough. But I think you would agree that our method is a little bit shorter and a little bit nicer. Okay, interpolation and extrapolation. So I realize that you're not in front of me and I can't see your response to this, but put up your hand if you've heard of extrapolation. And now put up your hand if you've heard of interpolation. My guess is most of you put up your hand for extrapolation. At least you kind of intrinsically have an idea of what that means. Interpolation, my guess is none of you have heard that before. So both of these methods, both of these mathematical methods, English people refer to as extrapolation. It's kind of a common word. The idea behind the difference in them is they're both guessing what a point is going to be based on a data set that you already know. It's where that point is. So let's refer to the picture on the right. If I have a bunch of data, and the data all goes from somewhere around A to B. So I'll pretend there's a whole bunch of dots here. And actually, just to go back a little bit, my data set here goes from X values from a little over 300 to almost 450, and from Y values a little over 250 to about 400. So if we're looking between known data points, so we have real data points that are on either side of the point we're looking at, then it's called interpolation. And interpolation tends to be a pretty good guess in most cases. Extrapolation is when we're looking for some kind of data point that is beyond any of the numbers that we have or anything that we can work with. So for instance, if I knew your height when you were 6 years old and your height when you were 8 years old, I could probably interpolate an approximate height for you at the age of 7, somewhere in between those 2 points. If, however, I was trying to interpret what your height was when you were 35, that would be extrapolation. That's going beyond the data points. And my guess probably wouldn't be fantastic. Okay, so in general, interpolation works out to be pretty nice. Extrapolation, if it's close to the data set, can be pretty decent, but it tends to get worse and worse as we get too far away, because realistically, even data that's linear on a short scale is not necessarily linear forever. So here we have a beautiful Mustang Boss 429. Its actual horsepower is 420 HP, and we want to know what it probably would have been advertised at. The reason that this is interpolation is because it's 420 actual horsepower, and we've got data from 300 to 440. So we have data on both sides of that. So from my graph, all I do is I say, okay, the actual horsepower is 420. So I basically go from x equals 420 up until I hit my line and then read off my y value, which is the advertised horsepower. So from my graph, it looks like it's just under 370, pretty close to 370. And if I plug it into my equation for my line of best fit, I get 369. Again, pretty close to 370. Now, is that actually correct? Is that what it was advertised as? I can look that up despite the fact that it wasn't on my chart. And it was advertised at 375 horsepower. So we're off, but we're not off by a lot. I think the fact that we guessed it within about 5 or 6 is pretty good. It's never going to be perfect, but then again, if we look back at our graph, not very many of our data points were right on the line of best fit. They're only going to be close or approximate to it. So I think we're doing pretty good with being in 5 or 6. And by the way, when I made up this example, I did not fix it to be that way. I just kind of took a value and it was what it was. Turns out it worked out rather nice. Okay, moving on to the Corvette 427. Now this was a pretty fast car. It has an advertised horsepower of 430. So obviously, or I shouldn't say obviously, but our belief would be that its actual horsepower would be a little bit higher than that. This one's extrapolation because we have a value that we're going to plug in of 430, despite the fact that it happens to be an advertised value and not an actual. But all the values that we have data for only range from about 275 to 390. So this one's beyond our data set. Not way beyond, but it's still beyond. That's what makes it extrapolation. So using my graph, again, you can see that the area that we're looking at up there on the line of best fit is away from the data points. There's not data around it, there's just data before it. So I'm kind of going backwards here. So I read the 430 off of the y-axis, go over to my line of best fit, and it predicts a value of about 500 for my actual horsepower. If I use my line of best fit equation and I solve for the actual horsepower, the x value, I can see that I actually get 500 again, which makes sense. The equation came from the line of best fit. Whether it's a picture or an equation, it should work out to be the same. But is this actually what the horsepower of the Corvette was? And it turns out that the actual horsepower for the Corvette was 480 horsepower. So we predicted 500. Actually, it was 480. So we're off by 20. At the same time, 20 out of 500 is about 4% difference. It's not really that bad, but tends to be worse doing extrapolation than it is doing interpolation, just because we don't have any data that's up that high to know that if the trend actually continues or not. Okay, this part on nonlinear regression, I mostly just want to show you what it looks like and to show you kind of how it's interpreted. So let's actually just fly over to the picture here. On the bottom there is a picture from Excel. The actual data points there are the same ones that we used in the lesson. And I put on here a linear, an exponential, a logarithmic, a quadratic, a power, and a cubic regression. And what I think you can see is that they're all pretty similar looking if I go down and look at those individual black lines. I don't even know which is which, to be honest. I am going to point out, though, that when I actually did the math behind it, there's only about a 2% difference between the best and worst line. So over this short range, all these regressions do okay. And truthfully, linear is probably the easiest one to work with. So it's the one that makes most sense to try. Now, I think you can see based on how some of these lines end in the top right, one of them looks like it's like plateaued and may even come back down. That's probably a quadratic regression. Some of them look like they're going up, but at different angles. So I think you can see that extrapolation using this method, or these different ones, are going to get way worse, or at least way different. Whereas the interpolation ones, they're never that far apart in the range of the data that we have. Okay, I thought I'd throw this one in here just for interest's sake. Here we have a sextic function. Get your mind out of the gutter, teenagers. Jeez. Okay, so this one is about 3%. This one's actually even better than the others for regression. It better matches the pattern they're taking. However, it's probably completely unrealistic. It's matching the dots that are there, but it doesn't necessarily predict what's going to happen before or after this. I think you can see just based on the bottom left there that it's going to suggest that it's actually going up as it gets smaller instead of down. So that seems weird that as actual horsepower went down smaller and smaller, advertised would get higher and higher. And likewise at the top right, you can see that it's starting to go downwards. So that's probably not a great way to do it. I did throw the actual equation in there if you're interested what it is. I wouldn't expect any of you to get it. In fact, I didn't really get it. I just had Excel do it for me. But I want to really drive home why we use linear regression as opposed to these others. It ends up being pretty much as good. And in many cases, at least for interpolation, it gives good results. Extrapolation, as soon as you're far enough away, any extrapolation is questionable. Okay. Finally, I'm just going to leave you off with a couple of slides here. Now, this one, um, definitely not linear regressions, definitely not exponential or logarithmic or quadratic. Uh, but the important thing is I do see a correlation. I do see a pattern. The pattern looks like it goes from the bottom left, goes up, down, overall getting a little bit larger. And the actual proper regressions for this, which I didn't do, I pulled these off the internet, look a little bit like that. Now, to be clear on this, I'm not sure what kind of regression that is. It's probably a combined function. So it could be a modified quartic function, if you've seen those. So something x to the power of 4, and then some other terms. It could actually be a sine or cos function times something. Um, it's really hard to tell. So the correlation says where's the pattern. The regression says what's the equation of the line that best fits the pattern. Where's our prediction model going? And we're going to stop there. Hopefully it didn't confuse you too much. Give the questions some attention. See if you can do a little bit of this on your own. And we'll see you in the next lesson.